Macroeconomics and slice.
Oh my.
This class is pretty easy because we have the best teacher.
Yeah, the best physics teacher.
And then
That makes me happy. Make sure to write it on all of my performance reviews.
Gotcha.
we'll do. All right. Slice talks about his friends the whole time.
No, he talks about Charlotte. That's what it is.
The city?
No, his wife, Charlotte.
Yeah, and his talks about his wife and his friends the whole time.
And
spends 10 minutes on slides and just spams through them.
and then you don't have like any, like on the tests, you haven't had a test yet? So,
Oh yeah, I got 46 on my first one.
yeah, he doesn't teach us. He doesn't teach us the materials. It's like you're expected to know all of this,
You gotta learn it on your own.
and some people.
Not easy.
Well, that's not the best.
Yeah.
And then Dr. Harshaw is just like,
Yeah.
I love how you're getting all this, all this on video.
I can edit it out if you'd rather.
I don't think it would really matter.
Yeah, it's like you're not gonna watch it, so.
Yeah. Hey, fourth person.
Oh, fourth person.
For what?
Yeah.
Great question.
I know these two guys are gonna not be here.
The question is, how much of it is sports versus how much of it is medical?
These two
how
are
much of it is
sports.
spring break?
I know these two are sports.
Okay.
Not him.
My brain isn't over in this one.
What do you have?
RD and then AL. And then I'll go, of course.
Alright, got it. I'm not gonna spoil it, but
Alright.
unless you want me to.
What's the first letter?
E. There you go.
Took me a second. Let me just code on this real quick. The fastest one on these was like
I
45 seconds.
I can't do crossword.
All right. I am wanting to teach today, so that at the very least there's a recording for those to watch.
No,
But-
five.
It's okay.
It's all right.
Hey, you're here. That's all I know.
Does anyone have any questions before we get started today? All right. Last time we were talking about torque, how it affects rotation, and also how sometimes if you don't want things to rotate, you have to make sure all the torques on something are balanced. We ended looking at this sort of a scenario, a situation where the torque on this object must be balanced, the object being the board of the seesaw. And the conclusion we arrived at in determining how this sort of thing is possible is that with the with the fulcrum positioned here rather than under the center of the board, the fulcrum is not supporting the board's mass adequately. And so if the board's center of mass is some distance away from the fulcrum, the weight of the board is actually a radius away from the fulcrum, and that, according to the torque formula, dang it, will generate torque if, again, the board's center of gravity is here, the weight of the board is acting there, that is some distance away, and that generates torque. In which case, the child on the other side is generating enough torque to cancel that out. So the thing we're going to start with at the beginning of today is the concept of center of gravity, alternatively referred to as center of mass. your book and your homework might alternate between calling that center of gravity, center of mass, abbreviated to either COM or CG. Those terms are all synonyms. I want to make that clear. And the center of gravity of an item refers to the point where its average mass is. And once you know where that spot is, you can tend to treat an object as if it were a single point mass located at that position. As long as an object's center of mass, center of gravity, is supported, you can treat the entire object as if it is supported. For instance, my water bottle, its center of mass will be within its literal center because it's symmetrical on both sides. And so as long as I'm supporting the center of my water bottle, it shouldn't fall over. And that remains true even if it's tilted slightly. As long as the center of mass is still over my hand, it will still level out and tilt back onto my hand. It'll only fall over if it tips so far over that its center of mass is no longer over my hand. To try to give a visual for that. This is normally, as it's sitting on my hand, its center of gravity being in its center. If it tilts slightly, but not far enough that its center of mass is not over my hand anymore, it will still remain supported. It'll tilt back over onto my hand. But if it tilts so far over that its center is not over my hand, that's when it falls over. The center of gravity of an object must be supported for it to, under normal circumstances, not try to rotate away from you. And this happens because objects like to rotate around their center of mass. It's the point where, again, you kind of treat the entire object as if it is one infinitesimally small dot at that point. So as long as that point is supported, the whole item's supported. If you exert a force directly on that one spot, it's as if you were exerting that force on the entire object. Some interesting examples of this that have been applied throughout human history are balance beams, seesaws, whatever you want to call them. As long as the center of gravity of the actual seesaw is supported, the whole thing will be level until you then add something else onto it and disrupt the torque equilibrium. But another interesting case are these bird toys. These things look familiar? Here, I thought everyone would have won one of these at Chuck E. Cheese at some point. Is Chuck E. Cheese still a thing?
Like, maybe.
Maybe barely. That's fair. Completely fair. Five Nights at Freddy's kind of ruined it. So, that toy is currently balancing on its beak. It's just a plastic bird, and it is weighted in such a way that its center of gravity is right in the tip of its beak. And for that reason, if you are supporting the tip of its beak with your finger, the whole bird will remain level on your finger. And the way that this is accomplished is that metal weights are placed in the tips of its wings and in its head to shift its center of mass forward. Where something's center of mass is depends on its mass distribution. If something is, a fairly regular geometric shape, its center of mass is usually somewhere in its center. But that's not always the case, because there are objects that are weird shapes and are made out of more than one kind of material of different density. So where something's center of mass is kind of depends. This oil drum, again, uniform object made out of one material and a standard geometric shape. Its center of mass will usually be in its center, so as long as the center of that drum is supported, it doesn't fall over. Does this toy look a little more familiar? Weebles waddle, but they don't fall down. How old do I seem right now?
I'm not American, so.
That's fair. This object is made out of two very specific types of materials, usually. the body of the object is usually made out of something that isn't very dense, like plastic, whereas this piece at the bottom here is usually made out of metal. And since metal usually is a higher density than plastic, that shifts the weight of the item down to a lower point. Most of the object's mass is located like on the lower part of it rather than on the upper part of it. And that affects where its center of mass is, that affects how it balances. The lower the center of mass is, generally the more stable something is, because it's easier to support. In this thing's case, because its center of mass is so low, you can tip it pretty much all the way over, but it's still, usually the surface it's on is still under that very low point. And so it doesn't usually fall over by itself. There are some boxing bags that'll use this technique in order to, you punch it over and then it just flies right back up if it's weighted in this way as well. And again, the bird toy. These things are mostly plastic, but they have metal weights in their wings and in their beaks so that more of the mass is located on this end of it such that it can balance right on its beak. So when I'm referring to center of gravity, these are the phenomena that I am talking about. The average location of an object's mass, which is often something's center if it is a uniform object. Uniform meaning it's made out of one material, doesn't have any holes, isn't an odd shape, or isn't a standard geometry. What am I trying to say? This is time, a signal that it's time for a water break. If an object is made of one uniform material and is one uniform geometric shape, its center of mass will usually be its dead center. But there are cases where that's not quite the case. Questions so far? Okay. As an example of some places where you'd see this, we build things that are able to take advantage of this in order to stay upright. If you've ever done any sort of research or interest in weapons, namely old weapons like swords and axes and stuff, the center of gravity of those things tends to be pretty important, because if you are building a sword, you usually want the center of gravity to be pretty close to your hand so that you have better control over the center of gravity and are better able to move it around. In the case of a hammer though, since most of the mass is in the hammerhead rather than the wooden or very light handle, the center of mass is in the head of the hammer, and as a result, the whole head of the hammer has to be swung around rather than to do something. Whereas a sword, the center is usually towards the center by design, and it's easier to swing overall. It doesn't take as much muscle to get a sword swinging as it does to get a hammer swinging of the same mass. Another weird place where this sort of thing comes up is actually tightrope walking, excuse me. You ever wondered why they, first of all, again, I feel like I'm dating myself a lot today. You guys seen this sort of thing before? Just checking? Okay, cool. You ever wondered why they hold on to that pole in order to stay upright when they're trying this sort of thing?
Balance.
It does help their balance. You ever thought about how it helps their balance?
They can like move it like a little bit to one side if they're leaning it more there than the other, maybe? No.
They can. You are absolutely correct. And basically it gives them a way to manipulate their own center of gravity. Because in the human body, your center of mass is usually somewhere in your torso. Exactly where just kind of depends. But when you're holding this pole, and I want to make it clear, this is not like a single piece of wood. These things are usually weighted. If they aren't solid metal, they're usually wood with metal ends. So it's not meant to be light. When you're holding that object, and again, it's heavy, you're able to manipulate your center of mass by moving it around. If you move it over here, your center of mass is now to this side, which would help if you were tilting to the right. You can move the pole in the opposite direction, and that'll help bring you back over there, and you just readjust as you're going. But another fringe benefit is if the ends of the pole are very heavy and they tend to droop downwards, that also tends to lower the point where your center of mass is. Because if you're carrying this thing and it's very long and very heavy and its ends droop down, as they tend to, that lowers your center of gravity, and that makes you a little more stable when you're walking on a precarious situation. If your center of gravity is very high up, it doesn't take a whole lot of torque to knock you over because that radius is bigger. The radius between center of mass and your feet is increased. And that's why trucks feel kind of unstable sometimes when you're driving them. They have usually a higher center of mass than sedans. But with this thing, lowering your center of mass, if it's physically in a lower point, smaller radius, less torque if you're wobbling, and it's easier to stay in control. So understanding center of mass can help when trying to understand and occasionally prevent rotation. Questions so far? All right. Now, for how this is going to mathematically affect the class, because this is, at least in part, a math-based course, objects like rotating around their center of mass. It's usually the most natural point for something to rotate around. If you throw something into the air and you notice that it spins, it's usually going to naturally try spinning around its center of mass. And that's why weirdly shaped objects tend to have a weird spin when you throw them into the air. If you throw, a marker, which is basically just a uniform plastic cylinder, since it's all one material and one geometric shape, its center of mass is likely in its middle, and it'll just spin about its middle when you throw it through the air. But non-standard shapes, or something with a weirder mass distribution, I'm trying to think of an example that I have on hand. Well, I can draw one. Let's talk about axes and hammers again. Dangnammit. Somehow I put down the marker that had ink in it. If you've ever gone to some sort of place or event where axes and hammers are being thrown, have you ever noticed that when you throw something like this, it tends to spin around the head of the weapon rather than around dead center or the handle? Yeah, it's because the center of mass is up here, and that's the point that it most wants to spin around. If you throw rocks or sticks, they also will rotate about that point, so just be careful when throwing anything, really. Objects like rotating around the center of mass, so knowing where that is handy. But where an object's center of mass isn't the only thing that can affect rotation. The axis that it's rotating through also affects rotation. On the board right now, I've got the same, I'm considering it a plank of wood, so same object 3 times. But since we live in 3-dimensional space, we have the X, Y, and Z axes that we could try to rotate this thing through. Rotate it through the Y-axis, and it would be like, spinning it on your finger like a pizza box. Rotating it through the Z-axis would be, well, you know what, I have a book, I'll just show it with that. So the first example is like this. Second example looks like this. And for third example, sorry, looks like this. Dang it. Same object, same center of mass, but you can choose which axis you choose to rotate that mass through. And not only does the position of the center of mass matter, which axis you choose ends up affecting how it starts spinning. Because objects, the mass of an object and where it is not only affects rotation, but the way in which something is spinning also ends up affecting rotation. An interesting twist. I'm going to take this book now, and I'm going to throw it into the air 3 different times, spinning it through a different axis each time. Trying to replicate the 3 ways that I've got it visualized on the board right now. And I want you to notice, as I throw it, how quickly it spins in each of those axes. If it spins quickly, that implies that it's very easy to make it spin through that orientation. But if it spins slower, that implies that it's more difficult to make the object rotate in that specific axis. So I'm going to follow the order in which I wrote these, and I'm going to throw it in the air 3 different ways. Just notice again the velocity at which it rotates. First, I'm going to spin it through this axis. Okay, got a baseline. Now, I'm going to throw it through this axis. Faster or slower? Let's do it again. I don't know why I bother throwing things when I physically can't catch them. So that's our baseline. Again, you're tracking rotations. And here's the second way. Got one vote for faster, sound right? Yeah, definitively, it spins more times when I throw it like this than when I throw it like this. It is easier to make the book rotate through this axis through its center than it is through this axis. And that's because of its mass distribution. Spinning through this axis, both halves of the book have to swing all the way around each time. But if I'm rotating through this axis, the radius from the axis to the edge of the book is smaller. The radius from the axis to the edge of the book is bigger if that is the axis than if this is the axis, where it's this radius. And that means that the mass is actually closer to this axis when thrown like this than like this. Yes, we're still rotating it through its center of mass, but this edge of the book is further away than this edge of the book is from that axis. And so, since overall the matter is closer to the axis, it's easier to spin it this way. The further away mass tends to be, the harder something is to make it spin, which again helps tightrope walkers, because if they have the pole and they spread the mass out, like they're adding mass and they're spreading it out over the length of the pole, they are harder to rotate, so they don't fall over. Here, being harder to rotate means that the book just spins slower. But I got a third axis here. This is actually going to be the really weird one. And I'm going to throw it through this axis. You might casually throw your cell phone like this, so pay attention. I want you to see if anything especially different happens this time around.
Also ends up rotating.
It is rotating, and you might be describing something. Might not be picking it out of your words correctly. Notice how it rotates. It changed. It does a back, I guess it's always doing a back flip, but then it adds like an extra turn in a different dimension, and it does like something like that. Yeah, let me actually, I'm gonna throw it with, this is, PC merchandise, of course, with the text facing this way, right side up. If it works right, ow. Upside down. Even though if it was just rotated 180 degrees, it'd be upside down facing backwards. Instead, it landed upside down facing you guys. Proof that it did an extra spin. It wasn't just spinning through this one axis. The axis you choose affects the rotation. And again, everything that's shaped like this does that extra backflip. You can kind of notice it with your phone too. That's it, be careful throwing these things. That's just a weird quirk of this shape when it's spinning. So, mass affects rotation, the location of center of mass affects rotation, and which axis you are making something spin through also affects rotation. We meaning physicists, combine all these things together into one concept called moment of inertia, optionally referred to as rotational inertia, and that's the term I'll try to use most often because that's the term in your book and your homework. Rotational inertia refers to how easy it is to make something rotate based on its mass, where that mass is located, and the axis you're trying to make the object spin through. This is the angular counterpart to normal inertia. Normal inertia indicates how difficult it is to make something change its motion in a straight line. Normal linear inertia limits how much you can make something's movement change moving forwards or backwards. If something has more mass, more inertia, it's harder to get it moving in a straight line, or harder to change its motion. If you have more rotational inertia, it is harder to make that object rotate throughout that specific axis. If you have less rotational inertia, because you have less mass, or you're picking an easy axis to make something spin through, it's easier to make something rotate through that axis. Now, to give an example as to why this matters to humans on planet Earth, once again, we have the disembodied bike tire of science. Do you want a wheel to spin easily or more difficultly? Easily. You want the wheel to spin well, quickly, efficiently, so that your vehicle can get where it's going very efficiently. And that's the reason why the axis of this wheel, the axle, is bolted right through its middle. Objects like rotating through their center of mass, so that's where the axle is located. And for that reason, the wheel's pretty easy to make spin about this specific axis. But, like with the book, we live in 3D space. There are other axes that we can make the wheel spin through. So, let's say that we assembled our bike wrong, and we hook it up so the wheels spin like this. Think this is nearly as effective? No. And this is because this motion makes more of the mass have to move than through this motion. Through this motion, most of the mass of the wheel is closer on average because the metal part, all these spokes, the spokes' center of mass is somewhere in the middle and only the actual rubber of the tire is furthest away. But if I spin it like this, the whole mass of the wheel, including the axle actually, that's probably part of the problem, has to move further. And for that reason, it's harder to make the wheel spin like this. I guess the third dimension would just be doing this, which also is not great. And so that's why we only bolt wheels to spin like this usually. So, how much mass something has is not the only determinant for how easily it will rotate. You also have to decide how you want to make it spin. And interestingly, every different shape and rotational pattern has a slightly different way to calculate its moment of inertia. I'm going to tab back and forth between these two slides. The uppercase I at the top of the slide is the symbol for moment of inertia. If it helps, you can just think of it as I for inertia, or angular inertia. I for angular inertia. And every different shape and every different axis that shape can rotate through has a slightly different way to calculate its moment of inertia. You will never have to memorize any of these. You don't have to memorize any formulas in my class. And especially, you don't have to memorize all these different ways of calculating I, because they're all different. I would provide you with a chart like this if you ever need one on a test. The official class formula sheet has this or a better chart already in it. I'm only showing it off right now to try to illustrate that the moments of inertia, or the rotational inertia for each of these shapes has a slightly different formula based on its shape, based on its mass configuration. If you wanted to tell me the rotational inertia of a sphere as it rolls, that formula is 2/5 times its mass times its radius squared. So as long as you know its mass and its radius, you can figure out the moment of inertia of a sphere, figure out how easy it is to make a given sphere spin. But let's say that that sphere was hollow. Now if it's hollow, that actually means that its mass is further away from the center of the sphere. Now, if I just took the same sphere and hollowed it out, it shouldn't have the same total amount of mass usually. So for these two spheres to have the same mass would be kind of a weird scenario. They probably have to be made of very different materials for that to be the case. But, you know, for physics demos, they do sell things like that. If these two spheres still had the same radius and still had the same mass, like say this one's made out of a denser type of metal, the formula for this one's moment of inertia is 2/3 mass times radius squared rather than 2/5. And that's because if the sphere's hollow, its mass is further away from its center. Whereas in this case, you know, most of it is in the center. Here, all of it is further away. Now again, this only works if their total mass numbers are still the same. But if the mass numbers were the same, and they still have the same radii, this one would have a higher moment of inertia, higher rotational inertia, just because it's hollow. It's harder to make it spin because it's hollow, as long as the masses are the same. Same kind of thing with cylinders. If the cylinder isn't hollow, its formula is 1/2 mr squared. If it is hollow, its formula is mr squared. You get rid of the 1/2. So if the masses are the same and the radii are the same, it's easier to make the solid one spin, because a smaller moment of inertia translates to an easier time to rotate, like how a smaller mass means you need less force to get it moving. Now, we only care about moment of inertia, rotational inertia for this class, to try to indicate how easy it is to make something spin. Tabbing back briefly just to highlight. Its variable is uppercase I, so if you see a formula with an uppercase I in it, that is what it is referring to. It's just I for inertia. It's a scalar because mass is a scalar, and it's just the angular counterpart to mass. And its unit is a weird one, kilograms times meters squared. But unlike some math calculations in this class, that's like the unit I'd ask you to know off the top of your head. Actually, I wouldn't have you memorize that one. It's a very odd one. But for the sake of completeness, that is what its unit is. Questions so far? Just for practice sake, you can ignore these two. We're just going to focus on these four shapes for right now. We are going to take one item out of each of those four shapes and calculate a sample moment of inertia for them. Just again to compare how easy it is to make a given shape roll. I take one solid cylinder, one hollow cylinder, one solid sphere, and one hollow sphere. They will all have a mass of 1 kilogram and a radius of 1 meter square. So this heavy and about this wide. If you're having trouble reading the chart on the board, that is completely valid. the same information is on the back page of your course formula sheet. So if you don't have yours with you, you can grab some of the extras up here if you want to see the formulas more closely. And for all these, we're going to treat radius as 1 meter and mass as 1 kilogram. We're going to start with the solid cylinder. So I-sil. The formula for that one is 1/2 mr squared. So 1/2 times 1 times 1 squared gives us 0.5. So that is the solid cylinder, not the hollow one. The hollow one has a formula, I'll call that IH dot sil for the hollow cylinder. The formula for that one is just mr squared, no 1/2 on the front. And so according to the formula, as long as the mass and radius are the same, the rotational inertia of the hollow cylinder is twice that of the solid one if the masses are the same. Meaning that the hollow one is twice as hard to get moving. It'll take twice as much torque, twice as much effort. Just because its mass is further away from the center. We've also got spheres. First we'll start with the normal sphere. Formula for that one is 2/5 mr squared. So 2/5 times 1 times 1 squared. And that comes out to 2/5, which is slightly less than 0.5. So the sphere is easier to make roll than the cylinder. And this is why, we tend to make balls perfect spheres. But then what happens if the sphere has the same mass but is somehow hollow? That's 2/3 mr squared. So 2/3 times 1 times 1 squared. So a hollow sphere, as long as the mass is somehow the same, has 2/3 for its rotational inertia and is more difficult to make spin than the solid one. Because again, if all of its mass is concentrated further away, it takes more torque to get it spinning. I'm mostly going through all this just to illustrate how the mass distribution affects this sort of thing. And that's going to play into the very last thing that I'm talking about today, which once we're done with that, we'll break for the weekend. Again, just illustrating a point. Since moment of inertia is the angular counterpart to mass, it would get used as the counterpart in any place where the linear formula would call for mass. Like for example, linear motion, force causes mass to accelerate. Angularly, torque causes objects to rotate. And that again depends on their moment of inertia, their mass distribution. We aren't actually going to use all of these in this class. I'm just trying to illustrate that wherever you normally see an M, I would show up in the angular version. But the only one of these we're actually going to focus on is this one for our very last rotational concept, and then we have spring break. Given where this is on this comparison chart, you know what, no mind games, I'm just going to tell you. That was the formula for angular momentum as a counterpart to linear momentum. Linear momentum, if you'll recall, rho equals mv, indicates how hard something is to stop when it's moving forwards in a straight line, based on its mass and its velocity. So linearly, momentum tells you how hard it is to make something stop if it's moving in a straight line. Angular momentum tells you how difficult something is to stop if it is spinning. Because even though it takes effort to get things spinning, once they are spinning, inertia compels it to keep doing what it's already doing, so a spinning object will keep spinning until forced to stop. Again, helps wheels spin. So that is the definition of angular momentum. Like its linear counterpart, the more angular momentum something has, the more strongly it is spinning and the harder it will be to change that rotation. And this is technically just a direct mirror of the linear formula. The L is the angular momentum for reasons that I don't understand. Again, physics ran out of letters a long time ago. But uppercase L is angular momentum, and that's equal to rotational inertia times angular velocity. Remember, that's what the omega is for, which again is the same as the normal momentum formula. Momentum equals mass times velocity, momentum equals mass times velocity. It's just angular velocity and rotational inertia instead of normal linear mass. So the same logic still applies. The more mass something has, the more effort you have to undergo to get it rotating at a certain speed. But once you have it at that speed, the more mass it has, the harder it is to make it stop. Which, again, if you've ever driven a truck, it and its wheels, once they get spinning, they don't want to not be spinning. And like linear momentum, angular momentum is also conserved if something changes from start to finish. Because like with linear momentum, you can't destroy it. It has to go somewhere. It has to cause something to be moving. And the benefit to, like, why we talk about this, why we care about this, is because this is what causes the gyroscopic stabilizing effect in a rotating object. If something is spinning, it wants to keep spinning, and specifically, since moment of inertia depends on the current axis that it's spinning through, a rotating object does not want to change the axis that it is spinning through. Once you get something spinning, it doesn't want to change anything, not even the direction that it is spinning in. This is, again, what causes gyroscopes to work. Because if I take this wheel and I make it spin through this axis, through this center axle, it does not want to tilt at all. It wants to keep spinning exactly like this. So if I hold it up by this rope while it's spinning, it won't fall over. It doesn't want to change its rotational axis. Its momentum, angular momentum, is compelling it, keep spinning exactly as you are and change nothing. And so it's just going to kind of continue fighting gravity until it loses steam and eventually falls over. And this is what keeps gyroscopes spinning, and is what keeps tops upright. If you ever played with a top, if it's not spinning, they usually tilt over onto their side. But once you get it spinning, it stays upright because that's the axis it's spinning through. It doesn't want to change. Furthermore, if anyone wants to feel this themselves, the wheel will literally fight you if you try to change its rotation. If I try to tilt it right now, it gets upset at me and fights me, and that's why it wobbles. It's why you don't want to just yank your handlebars when you're riding a bike. You usually lean into a turn. Sound familiar? If you want to feel it for yourselves, it's very odd trying to make this thing spin, or trying to make it turn. You're welcome to try that yourself. But for the sake of time, I want to go ahead and show you the one quick thing that I want to at least show you before spring break. It's okay if we have to save the math on it. Because angular momentum is conserved, like how linear momentum is conserved, once something is spinning, that total momentum doesn't change. even if the object's mass distribution changes. You ever notice figure skaters, like they'll go into a turn with their limbs all the way out doing this sort of a move, and then they'll pull their limbs in and start spinning super fast in place, and then they'll throw their limbs back out, exit their turn, and just continue on back in this pose? That is due to angular momentum. They have a certain amount of angular momentum going into the turn when their mass distribution looks like this. But when they pull their limbs in, they pull all of their mass in, and that reduces their moment of inertia. That doesn't cause their angular momentum to drop, it just causes their angular inertia to drop. And in order to keep their angular momentum constant, their angular velocity will rise rather than let their angular momentum drop. As the last thing we do before spring break, I will demonstrate this. I am not a figure skater though, so what I am going to do is I'm going to sit in this rotating chair and spin myself. You may have seen someone demo this in high school or on the internet. I have these weights, they're 1 kilogram each. I'm going to hold them in my hand to increase my moment of inertia more. I have more mass and I'm spreading it out over a wider area. So that's a bigger moment of inertia. And I'm going to make myself spin. Once I'm spinning, I'm going to pull my limbs in, and that's going to reduce my moment of inertia. My angular momentum doesn't want to drop, so if I reduce my moment of inertia, I speed up to compensate. And it's very uncomfortable. If you're ever dizzy, spin around in the opposite direction to fix it. Weirdly, dizziness is also caused by angular inertia, angular momentum, because you have fluid in your brain, and once it starts spinning, it doesn't want to stop. Dizziness is literally your brain fluid spinning around your brain. Which way am I going? Which way was I spinning?
To the left.
Thank you, that fixed it. So if you ever want to try that out yourself, you can. We'll pick back up with this on after spring break to make sure it makes sense. Sound good? All right. Let me know if you need anything. Otherwise, though, please have an excellent break. Stay safe out there.